Hello guys, welcome to the first video lesson on Allen Bradley PLC training course RSLogix 500 and 5000 series. My name is Sayyid Reza Fattahzadeh. I am one of the educators and site admin of plcgoods.com. In this video, after a short introduction, we are going to learn some important points about PLC hardware and its wiring. Then I will show you how a PLC executes a simple program. Well, what's the goal of this tutorial? See this pyramid? That's called the Industrial Automation Pyramid. At the lowest level, there are lots of electrical instruments such as push buttons, thermocouples, transmitters, sensors, and macro switches. These instruments can be used to define what type of outputs such as electrical motors or signal lamps should be turned on or off. But all these devices cannot be controlled by operators continuously. However, nowadays PLCs are used to achieve these tasks. PLC stands for Programmable Logic Controller. These devices help us to have automatic control in different industries. Besides PLCs, we can use some devices to visualize industrial processes such as human-machine interface or HMI displays. HMIs and PLCs can exchange data with each other over a suitable industrial network. So, the goal of this tutorial is to teach you how to program PLCs and their related HMIs to control and monitor industrial processes. In this tutorial, first the hardware of two different series of Allen Bradley PLCs will be explained and used. Let's see my PLC station. It includes a MicroLogix 1500 brick PLC and two analog input modules. Based on a future requirements, other types of available modules can be added to the right side of the PLC as well. Note that in each PLC station, a PLC can be connected to computers for programming with one or more suitable communication ports. Now let me introduce different parts of my MicroLogix 1500 PLC that is made by Allen Bradley Company. The status LEDs on the controller provide a mechanism to determine its current running status. There is a mode switch under the left access door with three options: Run, RAM, Program. I can connect my computer's serial port to here using a serial cable. Also, my PLC supports 12 digital inputs and these LEDs to show their states. Behind the bottom door, I can power my PLC with 120 or 220 AC voltage, and also it supports 12 digital outputs. These LEDs indicate digital output status. Let's review what I said. As you can see, based on the status LEDs, my PLC is on and it is in run mode. This is my serial cable to connect my PLC to my computer. Behind the left door, I can change its mode with this micro switch. At the top and bottom, you can see the digital inputs and output terminals. And these are two analog input modules that are connected to my PLC. Alright, let's do a very simple project. First, let me open the EKTS software. We can simulate simple industrial circuits with it. Now I want to use a switch to turn on or off a lamp. That's simple. Inside the EKTS software, we can assign a name for the inserted equipment. Let me use S symbol for the inserted switch and H for this lamp. Now I can test this circuit. As you can see, it is very easy to work with EKTS software. This type of diagram is called a ladder diagram. Let's see how a PLC can be used to turn on a lamp. First, I need to connect a switch and lamp to my PLC. So let me explain its wiring. Here are two screw terminals that provide a connection to an AC voltage L1 and L2 for powering the PLC's internal circuitry. The next terminal provides a path between electrical circuits and the earth for safety purposes and noise immunity improvement. This connection can be made for safety purposes. Other screw terminals on the bottom provide connection to output devices and are divided into 6 categories that can be identified according to their color and labels. The outputs of my PLC are relay types. For example, when it activates its first output, the connection between these two terminals is established, and as a result, the AC voltage reaches the lamp and turns it on. Also, my PLC supports 12 digital inputs, which are divided into 3 categories. Each category has a common terminal. This wiring shows how to connect a switch to digital inputs. When this switch is closed, the AC power reaches the PLC input, and then it will change the content of address I0 from 0 to 1. Now let's see how an input of my PLC can activate its first output to turn on the lamp. I need to transfer a program like this to my PLC. As you can see, this program is similar to a ladder diagram. So, based on this program, when the first input of my PLC is activated, it turns the first output on. To write and transfer this program to my PLC, I use RSLogix 500 to edit and generate a PLC program, and RSLinx software to establish a communication between RSLogix 500 software and my PLC to upload the program. Now let's run RSLogix 500. Click on this icon to create a new project. This window appears, asking me to select the processor type. Here we can assign a name to our PLC station. After that, I scroll down the list to find my processor type, which is MicroLogix 1500 LSP Series C. The left side of the screen shows the project tree window, while the right side of the screen is called the programming area, where we can develop or edit a user program. In the project tree window, double-click on the controller folder to open the controller properties window. Here, you can change the selected processor or click on the compiler, passwords, or controller communications tab to reveal more information about the processor type or drivers that will be used for establishing serial communication between the PLC and your computer. Now let's double-click on the I/O configuration. Until now, I have defined only my PLC with the address 0. There are several types of modules that I can use them beside my PLC. As you can see, I am using two analog input modules beside my PLC. Their part number is 1769 IF4. So let me find and insert them into my project. As you can see, the address number of the first analog input module is 1 and the next one is 2. These numbers will be used for input-output addressing during the PLC programming steps. Now let's write the first program. Let's click on this icon to create a new rung. As I mentioned earlier, the ladder language is similar to the industrial circuit diagrams. Let's add an open contact, which is called examine on as well. Similarly, let's add an output coil. Note that these 4 zeros inside the box indicate the first rung number. Now I want to connect this open contact to the first digital input, which its address is I:0.0/0. Type the address and hit the enter key. As soon as you hit the enter key, the description box appears to define a label. Let's type S as a label for the first input and then click on OK. I will explain this format for addressing later. Now let's define a label for the first PLC output terminal with this address O:0.0/0. Well, let's use H symbol for this output, like the created circuit inside EKTS software. Now click on this icon to verify files and then click on the next icon to verify the project. Then the user program is compiled, and after that the text bulletin 1764 appears under the input and output addresses. Now let's save this project. Now I need to use RSLinx driver to establish the communication between my MicroLogix 1500 PLC and my computer using this serial port. Let's launch the RSLinx Communication software. This software is a free application and does not need to be activated or a master key to be installed to run. Alright, let's assume that you do not have any drivers configured yet. Click on this icon, Configure Drivers. You will see this pop-up window. Select the RS-232 DF1 devices item under the pull-down menu to to create a new driver with this default name. Click on OK. Then you will see the driver configuration window. Here you can define the connection settings or just click on the Auto Configure item. RSLinx will test all the baud rate settings to detect the PLC settings automatically. If the setting detection goes well, you see an auto configuration successful message. Now let me click on OK and close this window. If all goes well, you should see your computer and the PLC you are communicating. Let me go ahead and launch RSLogix 500. I recommend using the Comms menu to open this window to check the connection settings. Now let's select the PLC and click on Download to load the program into its memory. Before that, I need to change the PLC mode from Run to Program. Now I can click on Download to transfer my simple program to the PLC. Well, the program has been transferred successfully. This message says, do you want to go online? Meaning, do you want to monitor the PLC program on your computer? Click on Yes. As you can see, my PLC is in programming mode, and this rotating ladder animation means the RSLogix is linked to the PLC and the program is loaded already. Move the slide switch from right to left to select the Run mode. If everything goes well, PLC goes to the Run mode and it displays the green power rungs. Now let me activate the first digital input with this switch. In consequence, the PLC turns on the LED. Alright, let me review how my PLC turns on the lamp with this wiring. When I press switch S1, the AC voltage reaches the first digital input. Remember, its address is used in the program. Then, PLC changes the status of this contact, and based on its program, which was similar to my circuit in EKTS software, it turns this output on. This address refers to the first relay output. So, my PLC connects these two terminals inside itself. In consequence, the AC voltage reaches the lamp and turns it on. Now, we are going to learn some important points about PLCs, which are a scan cycle, data types, and addressing. Then we will do a simple industrial circuit with PLC. Alright, I used my MicroLogix 1500 PLC and its connected switch to turn on a lamp or a LED indicator using this simple program. Now let me explain how a PLC executes its program. When a PLC is in a run mode, it stores the states of this and all other digital and analog inputs where it is called input image memory. Then the PLC processor executes the user program based on its current input image memory. Based on this simple program, the output will be off unless the first digital input is activated on the input image memory. Note that during the program execution, the processor does not change the status of physical outputs. Instead, it updates their status on its output image memory based on the logic of the user program. Finally, when a PLC processor reaches the end of the user program, it activates or deactivates its physical outputs according to the output image memory. After this step, the processor does some other tasks such as communication and housekeeping. Again, it reads and stores the status of all inputs on the input image memory to execute the user program for the second time. It does so over and over until the time a PLC is taken offline or it is shut down manually. This cycle is called a scan cycle, which takes about 5 to 10 milliseconds depending on your processor type and program size. We have seen how a program is executed by a PLC. In an industrial process, PLCs control all equipment and they need to know the status of a process by receiving and reading electrical signals. So how does a PLC stores this data? A bit is the smallest unit to store two states, 0 or false, 1 or true. For example, a digital input has only two states, so a PLC needs 1 bit of its memory to store a digital input status. A PLC stores a 0 when an input is inactive and a 1 when an input is active. A group of 8 bits is called a byte. 1 byte can store 256 states. See this table. We can store 0 with 8 zeros, 1 with 7 zeros plus 1, and similarly to 3 to 255. There are lots of standards to save data such as numbers, times, and dates, which will be told later. For example, we can use the 7th bit to store a number sign, 0 for positive and 1 for negative numbers. So, based on the new table and rule, I can store negative numbers as well. These numbers can represent an electrical signal value or some industrial parameters such as a motor speed or water level. If we need more precision, we can represent 536 states with 2 bytes, which are called a word. So based on the defined standard and number of bits, different data types can be stored in a PLC memory, like Boolean data, which has only 2 states, or integer numbers, dates, and other required data. Remember that I connected a switch and a lamp respectively to my PLC input and output, and I used their addresses in my program. Now let's see how we can address a specified input or output. First, let's start with the first digital output address. The letter O indicates that the address belongs to a PLC output. Then the file number is defined. For the output image memory, this number is 0 and it can be omitted. The colon is a separator. This 0 indicates the module that holds the actual output. Note that my system is consisted of 3 modules and their addresses are 0, 1 and 2. Now I want to refer to the first digital output of my CPU module, which its address is 0. The next number indicates the word number. As I mentioned earlier, a word is 16 bits and my PLC has only 12 digital outputs. So one word can store the status of my 12 digital outputs. So each bit of this word from bit 0 to bit 11 can store the status of my 12 digital outputs respectively. Note that by default, the word number of each module starts from 0. After the forward slash, the bit number of the word or the terminal number of the I/O module is defined. For example, in MicroLogix 1500 PLC, I have 12 output terminals. Hence, 0 refers to the first digital output and number 3 refers to this output, O3. Similarly, we can add SPLC input terminals. The letter I indicates that the address belongs to a PLC input terminal. Its file number is 1. It can be omitted during input addressing when I want to address the digital inputs of my PLC. My PLC's default addressing number is 0. It has 12 digital inputs and its word number is 0. Then I can refer to each digital input with a number from 0 to 11. Now let's see another example of PLC input addressing. Its first part doesn't need to change. Number 2 refers to this analog input module. This module supports 4 analog input channels and each channel uses a word to store its input electrical signal. Here I have referred to the third channel whose addressing number is 2. Then I can refer to each bit of the selected word. Note that if we don't define a bit number, it means we need the whole 16 bits that are used to store a number. Okay, let's do a simple exercise. Here is a simple industrial circuit to turn on or off a 3-phase motor. It can be divided into 2 parts, the control circuit and the power circuit. Obviously, when the start push button is pressed, the K contactor is powered and its normally open contacts are closed. Then the motor remains on until the stop push button is pressed. Now we are going to see how a PLC can turn on a 3-phase motor. Pay attention, PLCs can turn on small devices like signal lamps or contactors, but they don't have enough power to turn on 3-phase motors. So like the previous slide, we have to use a relay to turn on a 3-phase motor in a power circuit. Alright, I want to download this program to my PLC. This program is similar to the circuit which explained in the previous slide. In this program, I used 2 digital inputs and 1 digital output. Alright, let's write the PLC program in RSLogix 500. Well, let me select my processor type, which is MicroLogix 1500. Here I can see and define some properties of my controller. Let me click on I/O configuration to configure my hardware. My PLC's default address is 0 and I am using two analog input modules whose default addressing numbers are 1 and 2. Here we can see the input-output image memories. For example, this table shows the output image memory. This 0 refers to my PLC address, and this 0 selects the word number. Here you can see a list of instructions that can be used for programming. This instruction creates a new rung. I enter a normally closed contact and I also need a branch. Now I use these arrow keys to select where a normally open contact can be inserted. Again, I click on the Examine On symbol to place a normally open contact as holding contact. Finally, click on the Energize Output symbol. Now let's use the first digital input for the normally closed contact and use a stop symbol for that. Now I want to use the next digital input in my program. Let me show you another way for input-output addressing. After the I letter and the address of my PLC, in my case is always equal to 0, I can enter the overall bit number instead of entering the word and its bit number. Open the input image table. Each word has 16 bits, and for the first word, its bits number are 0, 1, 2, 3 to 15. The next word has 16 bits as well, but their overall bit numbers are 16, 17, and 18 to 31. For example, we can refer to this digital input with its word and bit numbers, which are 2 and 4 respectively, or just use its overall bit number, which is 36. Let me use this address to see its result in my program. Pay attention. For the next slot number, the overall bit number will start from 0. Let's use the second digital input to activate this contact. This contact will function like a start push button. Alright, similarly, we can assign an output address to this output energize instruction. Let me show you another way. Open the output image memory table. Here we can select the first digital output to define a symbol, then drag and drop it on the output coil. Also, I need a contact of this output as the holding contact. So, I use this output address for this contact too. Now, let's verify the project and files to make sure there isn't any error in the program. As you can see, the control circuit on the left side and the PLC program on the right side are the same. On the left side, I can activate the push buttons by pressing them, But on the right side, the states of the contacts on the program change based on the PLC inputs. Now I need to use RSLinx software to download the program to my PLC. Well, my PLC is detected. Now let's do the download. I need to change the PLC mode to program before the downloading. I also need to save it on my computer. My PLC is in program mode. Let me change it to run mode. OK, let me sort my computer screen for a better view. Obviously, on the left side, I can turn the three-phase motor on with the start push button. Similarly, I can turn on the first digital output by pressing the start contact. Similarly, I can stop the motor by pressing the stop push button and turn the lamp off by activating the stop contact. At this point, the project is done and tested successfully. Now let's see how RSLogix Emulate 500 software can be used to test the program without any physical PLC. Then we will start with instructions with normally open and close contacts. Alright, let's see how we can test the program without any PLC. First, let's click on Verify File and Verify Project icons to ensure that there isn't any error in the program. Now let's save the program. Here I need to assign a name for the program and at the bottom assign a name for the processor. Now let's open RSLinx, click on Configure Drivers and select SLC 500 Emulator driver. Now click on Add New. First, I need to define a name for the new driver. Then let me write number 0 in the station name field. As you can see, the driver is created here, but I don't have any processor detected. Now, to have a virtual processor on my computer, I launch RSLogix Emulate 500. Now let's open the PLC program which I saved it before. Now let's select a number for the new virtual processor. Remember, I used 0 before, so I should write another number like 1 as the station name for the new virtual processor. Obviously, RSLinx has detected a virtual processor. If I open another program with RSLogix Emulate 500, RSLinx will detect it as another virtual processor. Now in RSLogix software, I can select the virtual processors which are created right now to test the programs. You might see this message, not able to start emulator. Well, I installed my software on a Windows 7 with 32-bit. To resolve this problem, I close all opened software, then right-click on my software icons like RSLogix 500 to select Properties. Go to the Compatibility tab and select Windows XP Service Pack 3. I do this process for RSLinx and RSLogix Emulate 500 software too. Note that I only need to do this process once. Now let's open RSLogix Emulate 500, RSLinx and RSLogix 500. Let me open the saved program and transfer it to a virtual processor. Now the program is transferred successfully and it is asking me, do you want to go online? Now the virtual processor is in program mode. Let me open RSLogix Emulate 500 and change the processor mode to run mode. To change the state of each input, I can right-click on the desired input address and select the toggle bit item. We can test our programs with RSLogix Emulate 500 if we don't have any real PLC available. As you can see, the output is on. Let me turn it off by changing the state of the stop contact. Now let's learn instructions that can be used for PLC programming. You can test programs with your PLC or just simulate them on your computer with RSLogix Emulate 500. Let's start with the normally open and closed contacts. These contacts work like normally open and closed push buttons, but here is an important point to know. See this PLC wiring in which two normally open push buttons are connected to two digital inputs. Their addresses are used in the program to turn two lamps on or off, which are connected to two digital outputs. In normal conditions, this contact remains open because its related input address is inactive. So the first digital output and its related lamp is off as well. In the second line, this normally closed contact is used. In normal conditions, its related PLC input is inactive and it remains closed. So, at this line, the virtual power is reaching the second output and it turns it on. If I press the two connected push buttons, the AC voltage will reach to the PLC inputs. Then the processor will change the state of the contacts in the program. So the first contact will be closed and the second contact will be open. In consequence, a PLC will turn on the first lamp and it turns off the second one. Now let's have the previous program with a little change in its wiring. Here I have used two normally closed push buttons. Now the AC voltage can reach the two digital inputs. In consequence, PLC changes the state of related contacts in the program. So the first contact will be closed and it turns the first lamp on. For the same reason, PLC will turn off the second lamp when the S2 switch is in its normal state. Pay attention, I have not changed my PLC program, but notice that the overall performance of a PLC program can be changed by changing the PLC wiring. Alright, let's test this program. Let me open the input image table. Here, I can define a symbol for the selected input. Similarly, let me use the output image table. Now let's test the program. Now I can either test the program with my PLC or RSLogix Emulate 500. I prefer to use my PLC. Now let's transfer the program to the PLC. Well, I need to select the program mode. Let's open the input and output image tables to monitor the state of each input or output. Let's select the run mode. When the second digital input is not activated, this normally closed contact transmits the virtual power. This point is shown by the two green strips around the contact. Therefore, the second output is activated, which causes the red lamp to turn on at the beginning. Now let's activate both digital inputs. Obviously, at this time, only the first output turns on. Okay, until now, we have seen different ways to detect the state of digital inputs and outputs. The first way is using the related LED on the processor panel or checking the state of its connected devices such as signal lamps. The second way is when a computer is online mode, we can use input-output image tables or check the green stripes around the instructions. Now let's continue learning the bit instructions such as the latch and unlatch outputs and one-shot rising and falling. Then we will learn about some basic logics and finally we will do a simple project. Let's start with a latch and unlatch instructions. In the PLC wiring, I have connected 4 push buttons to the digital inputs, but I have used only 3 of them in this program. Like industrial circuits, suppose we have a power line. The first output is off unless I press the first push button S1 to activate the first normally open contact with this address. In the second line, I have used a latch instruction. This instruction is only used to turn on Boolean variables like digital outputs. So based on this program, if I press the third push button or S3, the second output will be on. Note that if I release S3, the output remains on. In the last line, I have an unlatch instruction. It is only used for turning off. So if I activate S4, PLC will turn off the second output, and if I release that, it remains off. Pay attention. You can recognize latch and unlatch instructions by the letters L and U. Now, let's test this program. You are expected to be able to write a simple program similar to this by yourself. Otherwise, please watch the previous videos. You can insert latch and unlatch coils the way I do. Now, I use the second output for the latch and unlatch instructions. Now let's compile the program and transfer it to the PLC. Let's change the PLC mode to the run mode. Obviously, in the first line and based on the state of the first digital input, I can turn on or off the green lamp which is wired to the first digital output. Based on the second line, the next push button only turns the red lamp on, and when I release it, the red lamp remains on. Finally, based on the last line, the next push button only turns off the red lamp. Obviously, if I press the last push button again, the red lamp remains off. Now let me remind you of another point. Sometimes for maintenance purposes, or when a switch or sensor which is wired to a PLC is defective, we can change the state of that related input image memory bit with a computer. As an example, let me right-click on this digital input address and select Force On. Obviously, the green lamp is turned on like when I press the first switch. Naturally, this way of changing any input image memory bit cannot change the input voltage on any digital input terminal. It only allows us to change the input image memory. Now let's use the force on command to activate the second and third lines. In the second line, the PLC turns the red lamp on, but in the next line, the PLC turns it off. Remember that PLCs update their physical outputs at the end of each scan cycle. So if the state of an output is changed several times during the execution of a program, the state of a last bit is used to update a physical output. Note that when we use force on option, the message forced installed appears. Also, the forced LED on the PLC is turned on automatically. Now let's continue this video with the other bit instructions. One-shot rising and falling. This program is similar to the previous program with the same I/O hardware wiring. So one of the advantages of using PLCs is that we can change the program logic without changing the wiring diagram. Obviously, I have used latch and unlatch coils, but a one-shot instruction is inserted in the second line as well. If I activate this contact, the virtual power will change from 0 to 1 behind the one-shot instruction. After that, I will have a pulse at the output of this instruction, which it can turn the green lamp on by this latch instruction. Pay attention, the one-shot instruction is not sensitive to the state of a virtual power. Let's test the program. I have inserted two normally open contacts and unlatch and latch coils. Now let's add a one-shot instruction to the second line. This instruction needs a bit of memory to work correctly. Here you can use a bit of binary memory or a bit of output image memory. Naturally, it is better to use a bit of binary memory because we need the output addresses to control industrial processes and the numbers of outputs are limited. Well, let's use the first bit of binary memory. Okay, let's test the program. My PLC is in program mode. Let's change it to run mode. Based on the second line of the program, let's turn on the green lamp with the second switch. Now, based on the first line, let's turn off the green lamp. Obviously, the second switch is activated, but its related output is off because, as I mentioned before, the one-shot instruction in the second line is only sensitive to changes in the state of a virtual power. So if I want to turn on the green lamp again, I should deactivate it and activate the second digital input. Alright, we have seen how a one-shot instruction works. If we need to use rising edges in a program, we can use the one-shot rising instruction. This instruction needs two bits. One bit is used to store a state of a virtual power, like the one-shot instruction, and the second bit is used as the output of the instruction, which can be used in other lines of program. Similarly, one-shot falling instruction can be used to detect falling edges. So at this time, this bit of binary memory produces a pulse. Pay attention, if these instructions are used several times in a program, their storage bits must be different together. Otherwise, they won't work well. Okay, let's rewrite the previous program using a one-shot rising instruction. Here, let's use the bit number 3 of my binary memory and then use that in the next line to turn on the output. Well, this and the previous program are equal. Try to test it. Similarly, you can insert and use one-shot fouling instructions from here. Alright, until now I have explained some basic bit instructions. Now you can write and test basic logics such as AND, OR, and XOR logic. For example, in the first program, PLC will turn on the output if and only if both digital inputs are activated. Try to test and explain these basic logics. Now let's do a simple project. See these three conveyors, which are physically hooked up in a series configuration, where conveyor number 1 feeds parts to conveyor number 2 and conveyor number 2 feeds parts to conveyor number 3. Each conveyor should have its own individual start-stop station push buttons. Also, there will be one emergency stop push button placed strategically to stop all three conveyors. Finally, conveyor number 3 must be running to start conveyor number 2 and conveyor number 2 must be running to start conveyor number 1. This wiring can be used for this project. The first digital input is used as the emergency input. S2 and S3 push buttons are used to stop or start conveyor number 1. Similarly, S4 and S5 are used for conveyor number 2 and the next switches are considered for conveyor number 3. Also, we need 3 contacts. Each contact can turn on a 3-phase motor with a power circuit like this. Now try to write your program for this project and test it. This is my solution. Obviously, I used the emergency input to stop the conveyors at the beginning of each line. This part of my program can start or stop each motor. Note that this normally open contact should be activated to turn on the second output, whose address is referred to the third output. So, to turn on the second motor, the third motor should be on already. Similarly, the second output should be on already to turn on the first output. Alright, let's test the program. Obviously, I cannot turn on the first output by pressing its related start push button because this contact of the second output is still inactive and open. Similarly, I cannot turn on the second output because the third output is off and this contact is still open, but I can activate the third output. Obviously, its related LED on my processor's panel is turned on. Now I can turn on the second output and after that the first output. Also, each output has its own individual stop push button. Note that when I turn off the third output, other outputs are turned off automatically. Thanks for watching this video.